performance of OpenRack V3 AC/DC rectifier by Manuel and Sam from Infineon Technologies.
Hello everybody.
Hello.
This is Manuel Escudero. I will start sharing my screen.
Yeah, go ahead and
you.
share the presentation.
So you let me know when you can see my screen.
Yeah, we can see your screen now.
Okay.
Yep, all good.
All good, go ahead.
So I am Manuel Escudero, application engineer for Infineon, and here with us is also Sam Abdel, who is a lead principal for Infineon. And we will be giving you an introduction of the power supply we are working on in accordance to the specifications for the OCP rectifier version 3. So this is a bit of the agenda that we have prepared. We will discuss briefly a bit the requirements of the specification, the key requirements, not all of them. So the most important ones that are shaping a bit the decisions that we took in this design. And we will go a bit more in detail about the two main blocks of this power supply. So we will explain this deeper later. But basically, the power supply is composed of two blocks. So we have decided to go for a front-end Totem-pole and a back-end half-bridge LLC. So we will go a bit in detail in the design of those two blocks. And finally, we will cover a bit of the experimental results that we got at the moment. So we are currently, the project is still not finished, but we already got some preliminary results. So this is what we would like to share as well. So this is a very brief summary of the specifications. So here, maybe the most important or what we are putting a lot of effort is in the right side, in the graph of efficiency, that we consider and we think and we are finding that is a quite tough requirement, especially achieving the peak efficiency. So the curve of the efficiency has to be something like what we are drawing here. So this red curve and the blue curve is out of the analysis of the simulation tools that we have developed during these years. So we did this forecast of what we could achieve and what could be cost effective. And these are these curves that are fulfilling the specs. Quite on the border with a slightly margin for the tolerances. And yeah, one of the key aspects and what is making difficult to achieve this high efficiency is the wide range input. Although in the specification is quite clearly specified and there is a lot of focus in that is narrow output range. And this is true, but it's also wide input because of the 20 milliseconds hold up. And yeah, this is also making the design of the DC-DC converter a bit more tough. So yeah, it's wide input still. So this is one of the key points that we will see later in the next slides that is deciding quite a lot many of the aspects of this design. Some other interesting details that we have in this slide is some of the components that we forecasted to have in this project. So most of the components that are listed here are just the key semiconductor power switches. So we are not listing all the components we have. We are making a special focus in the key components that are making this power supply high efficiency. So we have here high voltage MOSFETs. So we have CFT7 in a TO247 package. So we are going for leaded packages in this project. For the main switches, for the high voltage, we are using SND for the rectifiers, for the low voltage rectifiers. Okay, and then we have silicon carbide, that is the IMZ 65R048 M1H. This is also in TO247 3-pin. So it's one of our latest silicon carbide devices. Yeah, and for the control, in this case, we are going for a digital solution. So we have a general purpose microcontroller, 2 in this case, each one of them for the different stages. So yeah, those were the forecasts of the efficiency that we could achieve. And we think our preliminary analysis shows that the way to achieve this very high efficiency is with these 2 blocks at a reasonable cost as well. So, so we have a Totem-pole in the front-end stage, sorry, and we have a half-bridge LLC for the back-end stage. And what we can see here is actually a photo of the running prototype. And we can see already some of the aspects that have been defined by the requirements that we were talking about before. So the hold up time, for example, is making us to put here these 3 capacitors. So we decided to go for a bus voltage of 410 volts. So we didn't want to go up to 450. And therefore we need this extra capacitance. But thanks to the requirements in the dimensioning of this power supply, we still have this space. So although it's occupying high percentage of the space of the rectifier, we are still fulfilling the overall dimensions. Then we can see that we have the EMI filter. So we have decided to bring the BAC input from the rear end of the power supply back to the could be the front end, where the fan will be sucking the air. And then we have the 2 stages in line. So we have the EMI filter. We have here in the middle of the converter, we can see the Totem-pole inductor laying on the side. And right by the right side of the inductor, we can see the TO247 Totem-pole devices. And right by the side, we have the LLC block. So we can see the resonant components of the LLC block. They are right in the middle of the converter as well. And yeah, so this is just an overview of how the hardware is looking currently. So we will go a bit more in detail now in the design of the Totem-pole in the first stage. So we have some experience already building blocks in Infineon. So we are doing this kind of demonstration boards already for some years. And out of this experience, so we know more or less what is to be expected from these topology blocks. For example, here we have for the Totem-pole, we released this demonstration board, I think 1 or 2 years ago. And these are the efficiency results experimental of this board. So we know what this board can do, and we know that we can achieve this target already with this topology, within this design. However, we also know that this is not enough for achieving the required target of this OCP version 3. So we know that we need to increase further. So we have to go up to these blue curves here. And but out of the experience that we gain in the previous blocks that we have been designing during this year, so we also know what are the limiting points and what are the losses that we have to improve in order to reach that target. Specifically here in the table on the right side. So we are making a bit of a breakdown of losses of out of our simulation tools of what are the main contributions in this converter currently, and what are the things that we want to improve now in this design. Specifically, I have highlighted here the losses contributions that we plan to improve. So mostly it's the conduction losses and switching losses of the wide bandgap switches. How do we plan to do this? Is reducing further the switching frequency of the converter. Before, the previous demonstrator was at 65 kilohertz. Here we plan to move at lower frequencies. So we plan to move to 45 kilohertz nominal. And we plan to improve as well the main inductor. And how do we plan to do this? Is going for a better material in the core and increase the number of turns, especially for high lines. So we know that the core losses are also a significant contribution in this 50%, 40% load range that we are trying to improve. The same with regard to the second module or the second part of the converter. We also have experience doing the half bridge LLC. We have done this last year, so this board is already available in for ordering in some distributors, and we know the efficiency that this converter can achieve with this design that we did back then in that time. We also know that this is still not enough for achieving the strong requirements of this project. So we have to improve still the power density, because this demonstrator is somehow slightly big for the target of this new power supply, and we have to still further to improve the efficiency. We also understand what are the key points to be improved in this converter. We know that the transformer was a limiting point in the previous design, and we know that the MOSFET conduction and the synchronous rectifiers were also big contributors in that design. Mostly the transformer is what we will try to improve here, also because of the volume. So the previous transformer was not adequate for the height of this power supply. Because if you have seen in the previous slide, so here the transformer is laying horizontal, but even laying horizontal is exceeding the 1U, so the 40 millimeters of the specs. And for the MOSFET conduction that we want to improve, there we will go for a lower RDS(on). Thanks that we are working in CBS, this doesn't affect almost much or almost at all the switching losses. We will gain just conduction losses, and we will go for a better RDS(on) as well in the synchronous rectifiers to improve conduction as well. As I mentioned before, the transformer was one of the key points of the, or one of the maybe weakness of the previous LLC half bridge that we released. If we want to achieve, so that board was very high efficiency for the standard of an LLC, but for achieving the 97.5 of the full power supply, still has to be pushed a bit further. So one of the key points is the transformer. In this case, we decided to go for a full planar solution. And this is what we see here. So this we have been designing in-house. So this we are doing in Infineon, in our group, because we also understand that the performance of the full system is not only about the switches. The switches are very important, but once the switches are optimized and they are near as much as you can do, what you need is the magnetic and the converter to be designed around the switches to take the maximum advantage that you can out of them. So that's why we also do our internal research in understanding the topology and the magnetics and the transformer in this case. So we have been doing these simulations. This is what we are trying to represent in these slides. So we are doing the layouts, and we are doing finite element simulations, and we have done several iterations of this full planar transformer. And yeah, we currently have improved the performance of the previous transformer in a lower volume with this kind of modular approach that we see here. So we can see that we have stacked PCBs. So this is a very modular approach where we can actually increase the power just stacking more pieces. and of course increasing the the size of the core. But it's yeah, quite interesting for extending the power of this rectifier later on. So once we have this module, this transformer, we can double the power. For example, putting twice this kind of transformer. So let's come to the preliminary experimental results that we already have. So the converter here we have just capture. So we have many more captors, but we have just included as an example this in the left side a capture of the PFC at full load. So we can see almost no ringing in the gate. The blue curve is the gate of the silicon carbide in this case, which is driven by 18 volts, 0 to 18. And we can see also the overshoot in the drain in green. That is also well within the rated limits of the 650 volts breakdown voltage of this device. So we see that is yeah, there is almost no stress in the device, and this is very important to guarantee the reliability and the efficiency of the converter. And what we see in the right side is a couple of example captures of the waveforms of the LLC. So we can see the current of the resonant tank in yellow. So we see that we are operating the LLC near resonance, which is usually the best operation point for efficiency. And here I have also captured the synchronous rectifiers voltage. So we can also see that the over voltage and the ringing in the synchronous rectifiers is almost inexistent. So it's almost nothing. This is thanks to the planar transformer and the very tight commutation loop that we have in the layout. And we can also see that very smooth waveforms in the BDS of the CFT7 in the primary site, thanks to the CBS operation. So it's also yeah, no overshoot at all, and we are operating in CBS. We can see here in the right side in the gate waveforms. So we see that there is almost no switching losses or no switching losses at all, because we are turning off with very small currents as well, thanks to the operation near resonance. Yeah, so those are the key points to highlight. We can also see that the resonance operation of this converter, we have chosen it to be around 93 kilohertz. This we can see in the capture more to the right side. So let's come to the efficiency results that we achieve. What we see here is that we are falling slightly under what we expected, what we simulated at the start of the project. Mostly at the 50%, because we see that at full load we are actually within specs, and we see that at light load we are actually also within specs. But we see that at the 50% we are still missing a little bit. And if we look at the captors at the right side, the thermal captors, we can already identify as well what are points that we have still to address, and what are points that we might need to improve to still reach in this planet target. So in the upper right side, for example, we see the hot area in yellow color or red yellow colors. This corresponds actually to the synchronous rectifiers and to the transformer. So we see that still we need to look for the better balance of switching to conduction loss in the synchronous rectifiers. So this is what we are currently working on now. So we are experimenting and trying to choose the right RDS zone for the balancing this efficiency curve and achieving the target. And what we see in the right bottom figure, what we can see in yellow highlighted is actually the silicon carbide switches. And the inductor, the boost inductor, is also in red, but mostly what is hot is the silicon carbide. Partly I have to mention, because these captors we are taking without a fan to identify which are the losses. So don't take this like this is the temperature of the converter. we are just running the converter without fan, so we can, we can target easily what is the limitations of the system at the moment. So the silicon carbide is running hot, so mostly it's switching losses, this we know. So we also have to experiment with a few RDS zones to see where we get the optimal balance of conduction to switching losses for that 50% of load efficiency point. And this brings me to the call to actions, where we are giving here a summary of the activities we are currently ongoing, as I mentioned, to further push the efficiency of this 50% load. So we are actually going down several paths. So we are investigating the effect of the RDS zone in the totem pole. We are also investigating how much the efficiency can be improved if we place silicon carbide in the LLC instead of CoolMOS superjunction. We are also thinking to modify the transformer ratio, because we know the core loss is playing a role. And other aspects that we still want to try out are moving around the resonant frequency to see also where we have the optimum point. And this is what we are bringing here. So for having a bit of feedback from the community. And I mean, we are open to share further material. We are giving here the contact of Sam after. He's currently the expert of Infineon in server and data center applications. So he's the main person of contact, and he's also with us here. So he will be addressing some of your questions here at the finish of the presentation. And this is the current status. And I think we can stop here for some questions. We have some more material. So mostly what we have is going in detail into the schematics, but I think we have 5 minutes left. So we might go into questions at this point.
Yeah, thank you very much, Manuel. This is Sam, and especially that you're presenting from Europe at this late hour. I mean, you're doing and sounding great at this hour. So, but I think before 2 seconds before we go to the questions, I think there you see there is Manuel done a lot of effort in the analysis and several iteration of this board and optimize. It's very small incremental, increases in the efficiency is helping, and that's why this is one thing that we really like to get the feedback from the community, where we can collaborate, and if anything that they have advice for us, we like to get this help. And I think that at the end we like to generate some material or hardware that we can share after we verify or validate. That's, I think, the story here. Yeah, please, if you have any question, you have my email address. You can contact me directly, and yeah, we're open for question now.
Caleb, do we have time for questions?
We're going into a break. If you guys do have, if you want to stay on for a couple minutes, there are a couple questions that did come in. We could go ahead and ask those, and maybe just a couple minutes here. Let's see. One came in: current trends for long life of the BBU base cells recommend a max charge of 4.1 volts per cell. How would this affect
Caleb,
your calculations?
Caleb, I guess this question was for the BBU, the previous slide presentation.
You're right. I just actually see that now.
I think most of this question I see belongs to the previous presentation. I do have one question, and it is that for the PFC circuit, did you use silicon carbide for for all the 4 switches or only one leg?
No. We are using CoolMOS. Here, maybe you can see it better. We are using CoolMOS C7 for the leg that is commutating with the BAC frequency.
So one leg is
CoolMOS
CoolMOS.
superjunction. The other leg is silicon carbide.
Okay, and then for the second converter, DC-DC, was there any silicon carbide, or was it?
It is planned to do with CoolMOS superjunction. We are studying. We are experimenting. No, this doesn't require. But we know that silicon carbide is bringing up a bit of efficiency.
Okay.
So it's not needed. But if you put silicon carbide, we know that we gain a bit of efficiency.
All right. Thank you. I think we are way out of time. We want to go take a break. I think there is a couple of questions for you on the FanTech. As people asking about what is the motivation of silicon carbide. Please go ahead and respond to them offline. And
thank you.
Thank you so much. I think we can take a break now and